Right, hello guys. Today we are looking at applications of chemical equilibrium. So in order for us to understand the applications of chemical equilibrium, we need to look at what is known as Chatellier's principle. Very important, this principle. So I have stated it for you here. What does it say? It says that if the conditions of a system in equilibrium are changed, the system will counteract or it will oppose the change and re-establish a new equilibrium. So which conditions are we talking about? We are talking about conditions of pressure, temperature, and concentration. So that is Chatellier's principle. It means we are having a system that is in equilibrium. Remember, in the previous video, we looked at something like this. We're talking about concentration versus time, and then we did something like this. So here we had concentration in moles per decicubic meter, and here we had time in seconds. Then we were saying we can have a reaction whereby the reactant, one of the reactants, the concentration decreases with time until a point where the graph becomes flat. So let us say this is A, and then we can have another one which starts from here and then it reaches the point where it's also flat. Let's call this one B, and then we can have another graph perhaps which is like this, and then let's call this one C. Then I can write my hypothetical equation there. So you can clearly see that A and C, these are reactants because their concentrations are decreasing as the reaction progresses. So it means my reaction would be A, gaseous A, plus gaseous C, reversible reaction sign. So this is a synthesis reaction. They are combining to form gas B. So what happens is that as the experiment, from the start of the experiment, we are having a certain concentration of A because it is a reactant, and we are having a certain concentration of C because it is also another reactant. But as the reaction progresses, the concentration of these two reactants decreases while the concentration of B increases because it is a product. Then we are going to reach a point here. Let's assume, for argument's sake, this is 30 seconds. We are going to reach a point 30 seconds where the system reaches dynamic equilibrium. Remember, we said dynamic equilibrium is the situation whereby the rate of the forward reaction is equal to the rate of the backward reaction. So this is dynamic equilibrium. Then let us say now at 60 seconds the system is disturbed. It is disturbed how? It is disturbed in such a way that the concentration of B starts to increase. And then if the concentration of B increases, because B is a product on its own, it means the concentration of A is going to decrease. And the concentration of C is also going to decrease until a point whereby these three re-establish a new equilibrium. Let me just do this line down here so that it can make sense. So there will be a point where a new equilibrium is established. Just indicate it like that. So we are having a new equilibrium here. So somewhere here, okay, somewhere here is where we are having our new equilibrium. So this is the new equilibrium. So let us just go over it very quickly. So initially, because this is a reactant, the concentration starts at a certain value and then it decreases with time. This one also decreases with time. But we are going to reach a point whereby the system is in equilibrium, where the graphs are horizontal. And then at the 60-second mark, there was a certain disturbance that was done to the system. So what does the system do? The system opposes that disturbance and then after maybe 100 seconds, it re-establishes a new equilibrium. But the equilibrium that it establishes now is not the same as the original equilibrium. It is a different equilibrium. Are we together there? Perhaps we can just make an example. Where you are seated right now, I'm assuming you are seated, can you just stand up? Right. Then can you sit down again? You are going to realize that when you stand up and sit down, the position where you are going to sit right now is not the same position as you were sitting before. Even if you can try, you can't sit at the exact same position. So you have now established a new equilibrium, which is different from the old equilibrium. Are we together there? So that is what we call Chatellier's principle. So we are going to look at graphs a little bit later on. Right. So in order to understand Chatellier's principle, let us look at an equation. So let us first begin by looking at Chatelier on pressure. So Chatellier's principle. When we are focusing on pressure, let us look at that first scenario. Right. So in order to understand this, I'm going to write an equation here. Carbon dioxide gas plus nitrogen monoxide gas, reversible reaction sign, is going to give me carbon monoxide gas plus nitrogen dioxide gas, and then delta H is less than 0. Let us say that is my equation there. I'm going to call it equation A. Alright. So we have carbon dioxide reacting with nitrogen monoxide to produce carbon monoxide and nitrogen dioxide, and the delta H is written as less than 0. So what does this mean? We need to understand something here. When you are given an equation like this is a reversible reaction. It means there are two equations that have been combined to form one equation. So we have two equations here. We have what is called the forward reaction. So we need to split them. You don't need to write them here. You can still just figure them in your head. So we have the forward reaction. For the forward reaction, what happens? The carbon dioxide reacts with the nitrogen monoxide to produce CO and NO2. And for this reaction, delta H is less than 0. So this enthalpy change, which is given there, the delta H that is given on the equation, whenever you are given an equation, whatever they write here in terms of delta H, it is representing the forward reaction. So this means the forward reaction is exothermic. Are we together there? So once I get this, I know that this is standing for my forward reaction, and then it means my forward reaction is exothermic. Are we together there? Then I have another reaction here, which is called the what? The backward reaction. So for the backward reaction, what is happening now? This carbon monoxide and nitrogen dioxide are reacting in order to form carbon dioxide and nitrogen monoxide. And then for this one, if we say for the forward reaction, delta H is less than 0, it means for the backward reaction, delta H has to be now greater than 0. It is the opposite. Are we together there? So you need to realize that these are the two equations that we are having, or when we look at Chatellier's principle. So now that we understand, I'm just going to erase this so that I can make space. Alright. Now, let us say you are told that what happens when pressure is increased. Pressure is increased obviously by reducing the volume. according to Boyle's law, you remember ideal gas equations. According to Boyle's law, the pressure of a fixed mass of gas is inversely proportional to the volume. So if we want to increase the pressure, we have to reduce the volume. Are we together then? That is at constant temperature. We have to reduce the volume. So what we are doing now, we are reducing the volume. It's like when you want to pump air into your bicycle, what do? You reduce the volume. When you reduce the volume, you are increasing the pressure in the pump. That is how the air is forced out. So here, what happens when we increase the pressure? So when you increase the pressure, what you need to do, the first important thing that you need to do here is to balance your equation, or to check if your equation is already balanced. So let us look at the equation and let us see what is going on. Here, I have one carbon on the left hand side, I have one carbon on the right hand side. I have 2 plus 1, which is 3 oxygens on the left hand side, and then I have 3 oxygens on the right hand side. Is it okay? I have one nitrogen, I have one nitrogen. So my equation is already balanced. But let us just put the coefficients so that it is going to make sense. So here I have 1, here I have 1, here I have 1, and here I have 1. Are we together there? So on the left hand side, I have 2 mole of gas. Or I can say I have 2 volumes of gas. And then on the right hand side, I also have 2 mole of gas, or we can still say we have 2 volumes of gas. What do we mean by this? We are saying we have 2 volumes because here, this is 1 mole of carbon dioxide plus 1 mole of nitrogen monoxide. So when I add the 2, I get 2 moles of gas. And then here, I have also 2 moles of gas. Remember, pressure only applies to gases. So whenever we talk about pressure, it means we are referring to gases. So I have 2 moles of gas on the left hand side, and I have 2 moles of gas on the right hand side. So it means there is no side which is at a higher pressure, and there is no side which is at a lower pressure, because they are equal volumes of gas on both sides. So if there are equal volumes of gas on both sides, it means the pressure is balanced. So even if I increase the pressure, nothing happens. If I decrease the pressure, nothing happens. So the answer to that question would be, there will be no effect. So reducing the pressure or increasing the pressure in this type of reaction has no effect. We are not going to see a change in the yield of any of the reactants or the products. I hope that makes sense there. Right, let's move on. Let's look now at a different equation. Let's look at a different equation where now pressure is going to have an influence. Let's look at the equation from the Haber process, the industrial manufacture of ammonia. So we are going to be having nitrogen gas reacting with hydrogen gas, reversible reaction. It produces ammonia gas, and then the delta H is less than 0. It means the forward reaction is exothermic. So if the forward reaction is exothermic, I already know now that the backward reaction must be endothermic. Alright. So obviously, like we said, we need to balance the equation. 2 nitrogens, put 2 mole here. So the nitrogens are now balanced. Then there are 6 hydrogens, so I put a 3. So my equation is now balanced. Are we okay there? Very good. Now, what is the effect? What is the effect of reducing pressure? What is the effect of reducing pressure in this particular reaction? Right, very good. So now, here, we know already that we have 1 mole of nitrogen gas. So it means on the left hand side, there are 4 mole of gas, or there are 4 volumes of gas. whichever you prefer to use, doesn't matter. Why am I saying there are 4? Because there is 1 plus 3. So there are 4 moles of gas here. And then on the right hand side, how many do we have? We have 2 volumes of gas. 2 volumes or mole of gas. Are we together? Right. So obviously, where we have a higher volume of gas, that's where we have a higher pressure. So obviously, the left hand side is already at a higher pressure by virtue of the fact that it is having 4 moles of gas already. Are we together there? Now, what is the question saying? The question is saying, what is the effect of reducing the pressure? So if we reduce the pressure, I want you to listen very carefully here. If we reduce the pressure, what does the system do? The system is going to oppose. The system opposes. Are we together there? So if we reduce the pressure, the system opposes. How does it oppose? It opposes by favoring the side that has lower pressure. So that is higher pressure. Because we have reduced the pressure, it opposes by favoring the side with higher pressure. So what do we mean by when we say by favoring the side? So normally, I like to write my equations like this so that it makes sense. To me, I like to write it like this. When forward reaction is favored, when forward reaction is favored, I like to write it like this. Just check how I'm going to write it for you there. When we favor the forward reaction, it simply means we are going to have a little bit or very small amounts of nitrogen gas. And we are going to have very small amounts of hydrogen gas. Because we are favoring the what? The forward. It means we are basically saying the nitrogen and the hydrogen, they are reacting to produce ammonia. And then what are we going to produce now? We are going to produce large quantities or a very high yield of ammonia gas. So that is how I like to picture it in my head, that if the forward reaction is favored, it means we are going to have small amounts of nitrogen, we are going to have small amounts of hydrogen, and we are going to have large amounts of NH3. Are we together there? Right. What about now when backward reaction or reverse? When backward or reverse reaction is favored. When we favor the reverse reaction, remember the reverse reaction is starting with ammonia. The ammonia is decomposing, it's disintegrating. So when you favor the reverse reaction, it means this one now is in small quantities as 2NH3. Then you put your arrow there. We are going to produce large quantities of N2 and large quantities of H2. So I like to picture this in my mind. So it helps me understand that, oh, it means when we favor the forward reaction, we are going to have high concentrations of ammonia in the system and low concentrations of nitrogen and hydrogen gases. And when we favor the reverse reaction, we are going to have high concentration of N2 and high concentration of H2, but very little concentration of NH3. So that is how I like to picture the situation. But now, what is the question saying? The question is saying the pressure was reduced. So, when you reduce the pressure, we talked about this before, we said the left-hand side is having 4 moles of gas and the right-hand side is having 2 moles of gas. So when you reduce pressure, you are going to favor the reaction with higher pressure because the system must oppose. So by reducing the pressure, we favor the side with higher moles of gas so that it increases the pressure because the system is supposed to oppose. So when we reduce the pressure, what does the system do? The system favors the reaction with higher moles of gas in order to cause higher pressure. So the reverse reaction with 4 moles of gas is going to be favored. Are we together there? What are the 4? These are the 4. So the reverse reaction is favored. So to answer this question, what is the effect of reducing the pressure? The answer is, according to Chatellier's principle, we are not qualified to just say the backward or the reverse reaction is favored. we need to quote the relevant scientists. So according to Chatellier's principle, I'm answering it now. According to Chatellier's principle, the system will oppose. The system will oppose by favoring the backward or reverse reaction, by favoring the backward or the reverse reaction with higher volumes of gas, and therefore higher pressure. Just want to make sure that it is making sense here. We have reduced the pressure, so the system opposes. How does it oppose? By favoring that reaction which is going to increase the pressure, which is the one with higher volumes of gas, which is the reverse. Because the reverse has 4 moles of gas, the forward has 2 more of gas. But we have not answered the question. To answer the question fully, we need to explain now to say, okay, so when I look at the concentrations in the system, if I analyze the system and I look at the concentrations, what is it that I'm going to discover? So you are going to discover that we are favoring the backward reaction or the reverse reaction. So this one is now going. So we are favoring this one. So this one is the one that is true in this situation. So what are we going to find out? We are going to find out there will be high yields of N2 and H2 and very low yields of NH3. So there will be very low yields of NH3. So it means, remember, the purpose of this reaction is to produce ammonia. Why ammonia? Why is ammonia important? Ammonia is important because we are going to use it in the industrial manufacture of fertilizers. Ammonium sulfate and ammonium nitrate fertilizer, they are made from this gas together with sulfuric acid and nitric acid. So we need ammonia. So it means now in the industry, they have a process. When we reduce the pressure, instead of producing the ammonia that we want, we are actually having a lot of N2 and H2 and less ammonia. So it means it is wiser to actually increase the pressure. Is it okay there? So I hope you understand what the meaning of this is. So what is the effect of reducing pressure? The system will oppose according to Chatellier's principle by doing what? By favoring the reaction that has higher moles of gas, which is in this case is the backward or the reverse reaction. So the reverse reaction is favored. When the reverse reaction is favored, it means we are having a little bit of NH3 and a lot of N2 and a lot of H2. That is why I like to write it like that in my head, so that it makes sense to me. I hope it also makes sense to you guys. Right, very good. Then now, let us say they ask you a question and they now say, what is the effect of increasing pressure? What is the effect of increasing pressure? Right. So, again, according to Chatellier's principle, the system will oppose. The system will always oppose. So, when you increase the pressure, what does the system want to do? The system wants to reduce that pressure. So it is going to reduce it by how? The system will oppose by favoring. The system will oppose by favoring the reaction with fewer moles of gas or fewer volumes of gas. In this case, which is the what? The forward reaction. So the forward reaction is going to be favored there because we have increased the pressure. So once we increase the pressure, the system opposes according to Chatellier's principle by favoring the side with fewer volumes of gas so that it can reduce the pressure. So in essence, what does that mean? We now refer to this equation in my head. It means we are going to have very high volumes or very high concentration, Last time I said yield, this time let me just say concentration. It's basically the same thing. We're going to have very high concentration of NH3 and very low concentrations of N2 and H2. So that is what happens there. I hope you understand how we apply Le Chatelier's principle on pressure. So you just look at whichever equation they give you, and then you look at which side is having more moles of gas, and then you take it from there. I hope you guys understand Le Chatelier on pressure. Now let's look at Le Chatelier on temperature. Le Chatelier on temperature. But for Le Chatelier on temperature, let us perhaps use a different equation. Let's use a different equation. Let us use hydrogen gas plus iodine gas to produce hydrogen iodide gas. So here we are saying this is Le Chatelier's principle. Le Chatelier's principle on temperature. Okay, so that is Le Chatelier's principle on temperature. So we are having that situation there. So obviously we are going to be told that here delta H is less than 0. This already tells me that the forward reaction is exothermic and therefore the backward reaction is endothermic. Then I need to balance my equation. So in order to balance my equation, I have 2 hydrogen atoms, then I need to put a 2. Then I have now 2 iodines, and then my equation is now balanced. If they ask for pressure, what happens when you reduce the pressure? It's like what we did originally. The first thing that we looked at, here there are 2 moles of gas, and on the right there are 2 moles also of gas. So there's going to be no effect when you either increase or reduce the pressure. I hope that is very clear there. Now, let us say they say, what is the effect? What is the effect of reducing temperature? Let us say the question comes like this. Right, so in my head, I need to write the 2 equations. So if I favor the forward, remember it's in my head. If I favor the forward, I'm going to have a little bit of H2 and a little bit of I2, and I'm going to have a lot of HI. That is if I favor the forward reaction. And for this forward reaction, sorry, there should be one error there. And then for this forward reaction, it is exothermic, because the enthalpy change is less than 0. It is negative enthalpy. Are we together? There is a topic, I'm sure you've already looked at it, where you look at what it means to say the delta H is less than 0. So this is what happens when I favor the forward reaction. But now, if I favor the reverse reaction, if I can look at B, if I favor the reverse reaction now, it means I'm going to have a little bit of hydrogen iodide, but this time I'm going to have a lot of H2 and a lot of I2. And then for this one now, delta H is greater than 0, it means it is now what? Endothermic. I hope you understand that. So I need to picture this in my head first. So they are saying, what is the effect of reducing temperature? When we say a reaction is exothermic, thermic comes from the word thermal, heat, exo, to excrete heat. An exothermic reaction is a reaction that gives off heat. That's one of the characteristics. We can look at an exothermic process. Let's just consider at home exothermic processes. When you are cooking, right now I know we are all cooking in one way or the other. When you are cooking, you cannot wear a jacket when you are cooking, when you look at the weather, because it's very hot, because you are going to start sweating. Why? Because the stove is going to give off heat. It is an exothermic process. It is not a reaction. Let's not confuse the two. Then there's a process, then there's a reaction. Another example of an exothermic process is when you look at a heater. In winter, we're going to be switching on the heater so that we can keep ourselves warm. So the heater gives off heat. That is an exothermic process. So an exothermic reaction, one of the characteristics, it gives off heat. You can actually feel the heat. So the heat is given off. So when the heat is given off, what evidence do we see when we are doing the experiment? If we are doing the experiment in a beaker, or in a conical flask, whatever we are using, if we are doing the experiment in a container, we're going to see that the container heats up, it becomes hot. So that heating up is evidence that heat is being given off. Are we together there? So that is what an exothermic reaction does. It gives off heat. So now, when we reduce the temperature of this reaction, what is the system going to do? According to Chatellier's principle, the system must oppose. Okay? The system must oppose. The system opposes how? It opposes by favoring. So according to Chatelier, I'm not going to write it just to save time. According to Chatellier's principle, the system will oppose. It will oppose by favoring. It will oppose by favoring the reaction which gives off heat, or increases the temperature. Which in this case is the forward reaction, which in this case is the forward reaction, which is exothermic. I'm going to explain this exothermic. There will be high yields. There will be a high yield. Yield is basically harvest, what we get out, the products, what comes out of a certain process is what we call yield, like in farming. So there will be a high yield of hydrogen iodide and low yields of H2 and I2. Right. Let me explain what I'm saying there. So what have we done? We've reduced the temperature. So when we reduce the temperature, the system is going to oppose. How does the system oppose? The system opposes by favoring the reaction which seeks to increase the temperature. We have reduced the temperature. The system opposes by trying to increase the temperature. How does the system try to increase the temperature? It favors the exothermic reaction, because the exothermic reaction is the one that gives off heat. It is the one that causes the process to heat up. So it is the one that is going to be favored. So in actual sense, we are basically saying this reaction A, subreaction A, is the one that is going to be favored. So when we favor subreaction A, which is the forward reaction, it means we are going to have a little bit of H2 and a little bit of I2, but we are going to have a lot of HI. So we're going to have a high concentration of HI, hydrogen iodide, in the container, and low concentrations of these two. Are we together there? Maybe some of you love pets. Maybe some of you love dogs. I had a dog that I called Rex. So it's one thing that I use to remember. Rex for me means what? Reducing temperature favors the exothermic reaction. That is how I remember it. So once I reduce the temperature, I know that I must favor the exothermic reaction. So therefore, if I am to increase the temperature, the opposite is true. We favor the endothermic reaction. Are we together there? So even if they ask you what now is the effect of increasing the temperature, when you increase the temperature, according to Le Chatelier's principle, the system will oppose by favoring the reaction which reduces the temperature, which absorbs heat. So when you increase the temperature, we are going to favor the endothermic. So it means what? When we favor the endothermic, we are going to have high concentrations of H2 and I2 and very low concentrations of HI. So I hope you understand the effect of Le Chatelier on temperature. So we've looked at the effect of Le Chatelier's principle on pressure. We've looked now at the effect of Le Chatelier's principle on temperature, which means we have now to look at the effect of Le Chatelier's principle on concentration. We have to look at Le Chatelier's principle on concentration. So I'm going to make another video a bit later where I focus only on the graphs. To be a video just focusing on the graphs. So Le Chatelier now on concentration. Le Chatelier on concentration. So let's look at an equation. Let us say we have an equation. Which equation can we talk about? Let's talk about sulfur dioxide gas plus oxygen gas, reversible reaction sign. We're going to produce sulfur trioxide gas. Right. And then obviously we have to balance. We know that by now. One sulfur on the left, one sulfur on the right. Then I can say delta H is less than 0. They are not all going to be less than 0, by the way. Some will be greater than 0. So 1 oxygens, there are 4. Then here there are 3. So a question like this, an equation like this can be a bit tricky to balance. But what you just need to make sure of is that you must make sure that each atom is in the even number range. So 3 is odd. So if 3 is odd, we have to make it even. So I can put a 2 there. So I know now that I have 6 oxygens. So if I have 6 oxygens, then I have 2 sulfurs. So the fact that there are 2 sulfur atoms here, I must also put a 2 here so that the sulfur can also be 2. So 2 sulfur, 2 sulfur. Then these are 4 oxygens plus 2, which is 6, and these are 6. So my equation is now balanced. Again, if they say what is the effect of increasing or reducing pressure, here there are 3 moles of gas, there are 2 moles. So you remember that concept. Now, let us say the question is, what is the effect? What is the effect of adding oxygen to the container? Let's say they are in a container. Then we are adding oxygen. So when we add oxygen, what have we done? We have intentionally increased the concentration of oxygen. Can you see that? So again, when we are answering, what do we say? We say according to Le Chatelier's principle, according to Le Chatelier's principle, the system will oppose by favoring the reaction which we have increased again, we have added concentration. So it will favor the reaction which reduces the concentration of oxygen. It will favor the reaction which reduces the concentration because we have added oxygen. So the system opposes by favoring that reaction which reduces the concentration, which is the forward reaction. Because you can see that the forward reaction, if you look at it here, the forward reaction has no oxygen. So if we want to reduce the concentration of oxygen, we favor the forward. So the forward implies what? Which one is the forward? The forward is the one where we have little amounts of SO2 and little amounts of oxygen, but we have high amounts of SO3. So it means if we reduce the concentration of oxygen in the container, the system is going to oppose by favoring the forward reaction. This forward reaction reduces the concentration of oxygen. Instead, what does it do? It increases the concentration of sulfur trioxide. Do you understand it there? Then the same applies. If we reduce the concentration of oxygen, once we reduce this concentration, let's say there's another question there which tells us that the concentration of oxygen is now reduced. What does the system do? The system will oppose. It will oppose by doing what? By favoring the reaction which increases the concentration of oxygen, which means it is now going to favor our backward reaction. And when our backward reaction is favored, it means we are going to have high concentration of SO2 and high concentration of O2 and little concentration of SO3. Is it making sense there? Right, very good. So in the lab, there are actually very simple experiments or demonstrations that we can do to indicate Le Chatelier, so that we can apply what we have learned. We use what is called color changes. So color changes are very easy because you can see it's changing color, then you know that, oh, that is Le Chatelier in real life. So we want to talk about what is called the common ion effect. We want to talk about what is called the common ion effect. So I'm going to put something up here. I'm going to put something up. I hope it is visible from here. Right. So we have something like this. So we have something like this here. So when we look at this, we have this ion, cobaltous chloride, COCl4 2-. It is blue in color. It is blue in color, and then we have H2O, liquid. Then this one is pink, then 4Cl-. So I did not write the aqueous there. Right. So let us say the question is, what is the effect? What is the effect of adding water? Why are we calling it the common ion effect? We are calling it the common ion effect because we can see that on both sides we have common ions. There's an ion, chlorine is appearing on the left, and it is also appearing on the right. Are we together there? All right, we'll take it from there.